So just now I have shared my laptop screen, and I hope it is visible, right?
Yes,
Yes,
sir.
sir.
Okay. In the last class, we did discuss about elementary ideas behind quantum physics, and then we said that quantum physics must be based on three simple ideas. So one of them is de Broglie hypothesis. So what does it say? It says that all material particles are associated with waves known as matter waves or de Broglie waves. So it means when we say material particle, that means so it must have some geometrical shape, right? So it must have some geometrical shape and it must have some mass, and therefore linear momentum must be associated with the particle. Okay, and so this material particle, there must be corresponding, wave, and that wave is known as matter waves or de Broglie waves, because the de Broglie, first proposed this idea, and later on it has been proved in experimentally, that we had already seen in the last class. So according to this hypothesis, so nowadays we can call it, law or principle. The de Broglie wavelength, which is normally represented by lambda of the material particle, can be calculated by using this simple relation. It means the de Broglie wavelength lambda and the linear momentum associated material particle is related by this relation. H is the Planck's constant, which order is 10 to power minus 34. And once we calculate this de Broglie wavelength or material waves, and if it is comparable to the dimension of the system, which is normally represented by d, then we can say that the material particle or the particle can show its wave nature, or the wave nature of the particle can be observed. And if it is not comparable, one cannot ever or never, one never will observe the wave nature of the particle. So, so that has been, expressed this, mathematical expressions. Okay, so this is, very simple statement, and at the same time it is very powerful. So let's, see what could be the linear momentum of different type of particles, and hence the de Broglie wavelength. So here I have listed some of the well-known particles. So one of them is free particle. That means there is no potential. The particle is moving freely. Then the linear momentum will be mass time velocity. So everybody knows, right? And so I hope some of you or all of you might be knowing more or less about, relativity. Have you heard about relativity?
yes, sir.
Okay,
Yes,
so
sir.
those who have not heard, I guess, 10 plus 2, you might have come across relativity. So relativity means if the velocity of the particle is much, much smaller in comparison to the velocity of light, which is c, then that belongs to non-relativistic. And relativistic means if the velocity of the particle is comparable to the velocity of light, okay, the order of the magnitude. So if we have non-relativistic particle, so this is free particle. If the velocity is given, one can calculate the linear momentum. If the energy is given, for example, non-relativistic free particle, one can get also linear momentum. And if we have relativistic free particle, by using this expression, one can calculate the linear momentum, where E represents the energy of the particle, m naught is the rest mass of the particle. That means the mass of the particle at rest. So those who know relativity more or less, there will be length contraction, time dilation, mass reduction when a particle moves with velocity of light. So m subscript 0 represents the actual mass of the particle when the particle is not traveling. This is velocity of light. For example, electron, proton, neutron, these are subatomic particles, and when they travel with a velocity, right, one will have this relation. And some of you might be knowing about thermodynamics. That means if you keep a system at a particular temperature, right, one can observe the physics. For example, everybody knows about ideal gas molecule, a container containing ideal gas molecules. At certain temperature, one can calculate the physical properties or measurable quantity. One of them is the linear momentum, and it does depend on the temperature. The linear momentum of that thermodynamical particles, right, can be calculated by using this relation where k beta is the Boltzmann constant. So these are well-known different classes of particle, and therefore by using this relation one can calculate the linear momentum. And by using de Broglie hypothesis or expression, one can also finally calculate the de Broglie wavelength. Okay, and as we have seen from this expression, if it is comparable to dimension of the particle or system, then the particular system will show its wave nature. Otherwise, the particular the system will never show its wave nature. Is it clear to everybody?
Yes, sir.
So now,
Yes, sir.
in order to understand, better and to realize it, let's work out this simple problem. So you'll also find this problem from your assignment. In fact, it is one of the assignment problems. The question is like follows. You have to find the de Broglie wavelengths of these two different group of particles. So one is a 40-gram ball, right, moving with a velocity 30 meter per second, and an electron which is moving with a velocity 10 to power 7 meter per second. And here, once you calculate the de Broglie wavelength, then the next question is it possible to observe the wave nature of the above particle? If yes, why? If not, why? So you have to explain this. So what I can do, I will give 5 minutes to everybody. So you please calculate, and those who have answers, they can unmute and tell the answer. Okay, so your time starts now. So it's 2:15, let's say. Then I'll get back to you, or I'll give you 5 minutes as I said. So by 2:20, who will have the answer? Please unmute and tell the answer. Okay, is this clear?
Yes, sir.
Yes, sir.
Okay. So I'm listening you. So as I said, once you have answer, then let me know.
Hello, sir.
Hello.
Yes, sir.
So anybody has answer?
Yes, sir.
Yes, sir.
Yes, sir.
5.5 into 10 to the power minus 34 meter in case of ball and in nanometers in electron.
Then second one, 7.11 into 10 power minus 11 meter.
Yes, sir.
Yes.
So second one is 0.72 angstrom.
Yes.
So
7 in
second one
angstrom.
is
7 into 10 to the power minus
0.728
9.
and
Okay. Okay. So it all why the answer is varying?
Same
Somebody
answer.
says 0.728. Somebody says 7.2 into 10 to the power minus 11 meter or 0.72 angstrom.
Sir, 7.2
Accuracy of the
into
Planck's
10 to the power
constant.
minus
Yes,
9.
sir.
Well, it's because of the Planck's constant value that we assume.
Yes, sir.
Okay, okay, very good. That's the answer. Some of you might be using the Planck constant, which is 6.63 into 10 to the power
Yes, sir.
minus 34, and some of you have used some more accurate value like 6.626 and so on. Okay, but so those answers are correct. Okay, so the first case. So this case. So what is lambda?
5.5 into 10 to the power minus 34.
5.5 into 10 to the power
Minus 34 meter.
34 meter. Very good. And the second case?
7.2 into 10 to the power minus 9 meter.
7.2 into 10 to the power 7.28. You can write 7.2, 7.3, or you can have 7.28. Okay, because if you approximate it, it will become 1 into 10 to the power
minus 9 meter.
no, it should be minus 11
Sir,
meter.
11. 11.
Yes, sir. 11.
Okay, so but we are interested in the order of magnitude, right? So so here, and in terms of angstrom,
0.728.
0.728 angstrom. 0.728 angstrom.
or we can say it's 0.72 angstrom. Okay, so
Yes, sir.
and then we have calculated. So now answer the question. So the first case, the ball, will it show its wave nature? If
No,
yes, why? If not, why?
No, sir.
Why not?
Sir,
Sir, it
because
will
the
show, but
dimensions
we
of
cannot
the
observe.
wavelength is not close to the dimensions of the ball, but
Very good.
in case of
Okay.
electron, it is close to the dimension of the
Okay. Okay. So that's it. So the order of the magnitude lambda is, I can say 10 to power minus 34. You can make out 10 to power 33. Okay. And what is the dimension of the ball in the in meter? If I say, so you can use let's say the smallest ball will be table tennis ball, or you can say the tennis ball or cricket ball. But the order, or you can have football. So it would be the dimension won't be bigger than 1 meter, right? The dimension is dimension will be 10 to the power minus 1 meter. So now the dimension of the system is much greater than lambda. Hence, the ball which is moving this speed won't show its wave nature. Whereas the electron case, will it show?
Yes, sir,
Yes,
it
sir,
will.
it will show.
What is the
Yes, sir.
dimension of the electron? The diameter of electron is, we call this is, we can say, diameter of electron. Okay, this is in fact represented by a very nice symbol called R naught, Bohr's radius. That R naught, it is order of angstrom. Okay, so R naught represents Bohr's radius, so it is order of angstrom. So this case, the dimension of the this is comparable to dimension of the systems. Okay, so the electron which moves this velocity will show its wave nature, and in fact the electron actually moves within. Everybody knows that, in our high school physics, we knew that, we have been told that in atom we have nucleus at the center, positive, and electrons, circulate with circularly orbital. Okay, so this case one can calculate the velocity, and the velocity is actually 10 to the power 7 if you calculate. So therefore, the electron we should not treat as a particle when they are inside an atom. It should be treated as a waves, and therefore we have electron cloud. You must have heard about sp-d orbital in your
Yes, sir.
chemistry. Okay,
Yes, sir.
so the S is spherical. That means electron distributed, uniformly in a spherical sphere across nucleus, and P, it's a dumbbell shape. What does it means? The so that will talk. So if this will be center of the nucleus, the electron, distribution will be like this. Okay, so so that's because the electron is no longer a particle inside an atom. So the similar type of problem we'll find in your assignment, which probably I'll post by today or maybe day after tomorrow. But don't worry, but we'll get sufficient time, to finish your assignment. But it is advisable to solve the assignment problems, parallelly to your theory class.
Yes, sir.
Okay. So now, so let's talk about the second pillar of the quantum physics. The quantum physics, should be based on the uncertainty principle proposed by Heisenberg. And some of you, all of you might be knowing the statement, but again, here we will not go or touch the mathematical formulation. Actually, there is a different, separate, books, that formulation of quantum mechanics based on uncertainty principle. That means mathematical approach. And in short or in summary, what does this mathematical, expression, tell us? That we cannot measure simultaneously both position and its corresponding linear momentum with unlimited or 100% accuracy. There must be some percentage of error. So this is the mathematical expression. Delta x error in measurement or uncertainty of the x component position, and this is the corresponding linear momentum. So that would be the optimal measurements. Okay, and similarly we have y component, because we live in 3 dimension, y and z. And then those who know, there is also fourth dimension. What is that dimension? The time. Okay, so the uncertainty principle also valid to time dimension. So that is delta t and delta e much greater equal to h over 4 pi. So delta t is the uncertainty of the measurement of the time and their corresponding energy. Okay, and this x p x y p y z p z time, energy, even if we have this is linear position, right? Yes or no? X, Y, Z. This is axis along Cartesian coordinate. X, Y, Z. This is called Cartesian coordinate, right?
Yes,
So
sir.
what we have, angular coordinate, polar coordinate phi, and so therefore, so delta phi into delta Lz greater equal to h over 4. This is the angular momentum, or there this delta Lz is the angular momentum, assuming the electrons are moving around the z axis and their corresponding angle, as I have represented here. So this. So these either x px, y py, z pz, t e phi lz, they are called canonical variable. Right? That means pair variables. So in our harmonic oscillator or coupled harmonic oscillator, if you remember that case, we said normal coordinates, right? So similarly, a term in physics called canonical variables. That means pair variables. So actually, this uncertainty principle, as we know, it is valid. Um, this, but apart from these, canonical variables, there are also other canonical variables. Okay, so that case also uncertainty principle is applicable, but we'll stick only one. Okay, so this delta x delta p x greater equal to h over 4 pi. Is this clear to everybody?
Yes, sir.
Yes, sir.
And let's say, like by using de Broglie hypothesis, we could make sure that whether a material particle will show its wave nature or not. Similarly, you might ask question, what kind of information we'll get if we impose uncertainty principle to quantum particle? Okay, and again, I would like to bring your attention that this is some level of summary, right? It's a summary, right? And much more detail is will take many classes. In fact, you can say 50, 60, 100 or whatever, but we are not interested that, because we only are interested the elementary things which are only applicable, which is useful to us, like the engineer students like you. So so uncertainty principle, if you remember, I said that quantization of energy is the consequence of the uncertainty principle that here we are going to discuss. So the quantization means that the energy level will be continuous, but quantization means the energy level should be discrete rather than
Discrete.
continuous. Okay, so when we say discrete, that means energy will be spaced like this. Okay, and then there will be minimum energy. This will be E1, this will be E2, this will be E3, this will be E4. So you are 1, 2, 3, 4, they are indexes for the corresponding energy level. Then you might be interested to know, okay, so this is discrete energy. What would be the minimum? Then suddenly you will say it's 0. But this is not 0. For quantum system or quantum particle, the minimum energy cannot be 0. And this is because of the uncertainty principle. So you can see here, right? So because we cannot allow this delta t will be infinity, right? And therefore there will be error in the measurement. And because the uncertainty measurement, so hence we have non-zero minimum energy. So in short, uncertainty principle gives guarantee the non-zero minimum energy of a particular system. And this minimum energy, which is non-zero, is known as ground state energy of the particle of our particular system. Okay, so the minimum energy in quantum language, quantum physics language, is known as ground state energy. That we'll also see when we'll solve some of the well-known quantum mechanical problems which are exactly solvable. That means by using mathematical approach, we'll solve it. That we'll see in the next chapter. But the question here is how the energy will be minimum or non-zero. Okay. So and since we are, as I said, that when we'll solve the some of the notable problem or a famous problem in quantum physics, there we'll see the discrete energy level and also the non-zero minimum energy or ground state energy. But here, since we are using uncertainty principle, we may or may not get the exact expression or the exact value of ground state energy or non-zero minimum energy, but it will show that the minimum energy cannot be 0. Some cases will get the exact ground state energy, and other case will not get the exact ground state energy, but both cases we'll get non-zero minimum energy. That means the ground state energy cannot be zero. So that's our objective. So let's work one by one. So let work. Everybody knows about simple harmonic oscillator. Okay. So let's you have quantum harmonic oscillator. So that case, and we have this uncertainty principle. Delta x delta px is greater or equal to is over 4 pi. Am I still audible?
Yes, sir, audible.
Yes, sir.
Yes, sir.
Okay, and here instead of writing h over 4 pi, I can write h bar. It is called reduced Planck constant, which values h over 2 pi. Okay, so therefore delta x delta px will be greater or equal to h bar over 2. So now we'll ask a question ourselves. What would be the error or uncertainty of x and px measurements? So that question when we'll ask, then the best answer will be that the error in the measurement of delta x will be the position value of the particle x, the order of the magnitude, and the linear momentum error will be px. Because we are getting measurement, right, of the position. Let's say one case we get, let's say 1 angstrom for the center. Second, from the measurement references, second case 2 angstrom, third case 3 angstrom, and again 1.5 angstrom, and then let's say 2 angstrom. And what we came to know that the particle position is between 1 to 3 angstrom. And what could be the maximum error in the measurement? That should be the order of the position. So similarly, the linear momentum, it cannot exceed this. Okay, and then so this product x and px must or it should be close to h over 2. You may ask question why it will be h over 2, because we are looking at the minimum energy. Got the idea? Yes or no? So this will be close to h over 2 because we are looking at minimum energy. So therefore, in order to get the minimum energy, so it cannot be less than h bar over 2. What could be the minimum value? The minimum value will be close to h bar over 2. Everybody understood? Yes or no?
Yes, sir.
So here
Yes, sir.
we said
Sir,
that.
please explain once again. I could not get this point.
Okay, so this relation we have seen, right? Then here we will ask question, what would be the error or uncertainty of x and px measurement? So suppose you are doing a measurement, okay? You have a reference point, you find particle, the position, let's say 1 angstrom from the reference point. Second case, 2 angstrom. Third case, 3 angstrom. Fourth case, 2.5 angstrom. Fifth case, let's say 1.6 angstrom from a reference point. Then you will conclude that the uncertainty of the measurement should be within this 1 angstrom to 3 angstrom. It cannot go beyond. So therefore, delta x will be order of x. And similarly, delta px, the error in the measurement will be order of px. And if we look at the minimum energy, then this delta x, delta px should have the minimum value. We cannot go beyond the minimum value. So therefore, x plus px value will be close to h over 2. It cannot be less than h over 2 because we are looking at the minimum value. Okay, so here the idea is that you have two parameters, and of course they are canonical variable. We will convert one variable to other. So using this relation, px will be h over 2x. So now substituting the value of px in equation here, the energy expression, what is the energy? The px square over 2m plus half m omega square x square. The kinetic energy, and the potential energy. So this is the potential energy associated with the harmonic oscillator that we have already seen, and this is the kinetic energy. So now using equation 2, if we substitute, so this will be a almost equal value this. So now what we got, they are the energy expression here. So note that, so this is in terms of the position. And since it is the minimum, so this is the minimum, and in order to have the minimum, we have to look at the first derivative. That means it should be 0 when you do the first derivative, x equal to x naught. That's so the minimum occurs. So do remember that whenever you have a function f of x, whether we'll find it is minimum or maximum, we have to first do the first derivative. You have to equate with respect to, let's say, at a point equal to 0. And then if the second derivative, that's f double prime fx, so it's normally called f prime x. If the second derivative is greater than 0 at this point, x equal to a, then this implies a minimum. And if it's less than 0, it implies maximum. Yes or no? So
Yes, sir.
Yes,
this is
sir.
the standard procedure to find out the optimal value, whether minimum or maximum. So exactly we are doing here. Okay. So let's start x equal to x naught, the minimum occurs, and there we'll have. So now what we observe that the x naught, the minimum, this error in the measurement will have s bar over 2m omega. Now we optimize this function at x naught. So you do the second derivative. I'm not going to do. You do the second derivative, and when you substitute, definitely find it is less than 0. So therefore minimum. So since you know at x equal to x naught, the minimum occurs, and therefore the x equal to x naught, the energy will be minimum. So that's exactly I have written. So using equation 3 and 4, the minimum energy will be here by simply substituting value of x naught in this expression. And once you substitute and simplify it, what we'll get? So this part will give half h plus omega, and this part will give half h plus omega, which is 1/4, which is half of h plus omega. So now this is not 0. So what we conclude that the quantum system or quantum particle should not have 0 minimum energy. It should have non-zero minimum energy, the ground state energy. And by accidentally, this is the exact ground state energy of a particle which follow harmonic, simple harmonic type of motion. Okay, and we'll do maybe next to next class how to calculate the discrete energy values called energy spectrum of quantum particle or of a system which contains quantum particle. So there we'll get the energy spectrum. Discrete energy will be n plus half h cross omega, where n represents the energy level. Okay, and more precisely, it is known as the quantum number that indicates a state of a quantum particle. That again we'll study when we'll solve the exactly solvable quantum mechanical problem. And if we substitute here, then you'll have h plus omega. So as I said, in some cases we may get the exact ground state energy. This is the classic example. When you solve simple harmonic oscillator or particle which follows simple harmonic oscillation kind of motion, and if it's a quantum particle, then it should have non-zero minimum energy. Is it clear to everybody?
Yes, sir.
So let's work out other problems. Okay, and this is hydrogen atom. So everybody knows that among all atoms, hydrogen atom is the simplest configuration. We have one proton and one electron. Okay, and as you know, the potential energy that electron feels can be expressed by this expression: E square minus E square 4 pi epsilon naught r, where epsilon permittivity of the free space. So why the negative sign is here? Because we have proton which is sitting here, and then electron, and electron is moving here around the, okay, so it is a plus E minus E. And the potential you can calculate. We have Q key over 4 pi epsilon naught. R is the radial distance. So here the proton charge is E and electron charge is minus E over 4 pi epsilon naught R. Okay, so this is minus E square by 4 pi epsilon naught R. Okay, assuming that free medium in between electron and proton. And the negative sign also indicates, you can interpret that since the electron is bounded, attracted by this positive proton, right? So therefore it indicates that the attractive nature of the potential. That means the proton will attract electron. Got it? Yes,
Yes,
or
sir.
no?
Yes, sir.
So now the same procedure. You have energy. So now you have radial component delta, and you can use also delta PR if you like. Okay, the same strategy. You have to minimize, and then what will get there, the epsilon naught is m square 8 pi square epsilon naught h cross square. And here I would like to point it out. We talked about the radius electron. So this, if you calculate, everybody knows the epsilon naught, h bar, mass of the electron, charge of the electron, then you'll find it will be order of angstrom, which is Bohr radius. So this of course is not zero. So in hydrogen atom case, you can also find that the minimum energy cannot be zero. But this case, okay, and if you solve the hydrogen atom problem, some of you might have been already solved by using Bohr's theory. So those who do not know, they can look at Bohr's theory for hydrogen atom. So this case, you must have this expression, where again n represents the quantum number or the discrete energy levels. And if you substitute n equal to 1, we have this expression. One negative sign will be minus this thing. And so if you look this expression, so this case, the ground state energy is not the exact ground state energy. Okay, so it is 4 times minimum energy obtained using uncertainty principle. Then you might make argue, why the negative sign is appearing here? The negative sign indicates here the electron is a bound state. Is the electron is bounded by the attractive force between electron and its corresponding nucleus or proton. Okay, but if you don't consider this negative sign, we'll have 4 times the minimum energy that we calculate using uncertainty principle. But the message here is that the quantum particle or the quantum system should have non-zero minimum energy of the ground, that is called ground state energy. And in harmonic oscillator case, that means particles that follow harmonic, simple harmonic kind of potential, by using uncertainty principle, one can calculate the exact ground state energy, whereas in hydrogen atom, the magnitude is 4 times greater than the actual ground state energy. But if you look carefully, all these variables, m square is appearing, pi square epsilon naught h bar square, pi square epsilon h bar square, all those things are appearing. Only the 4 times. Okay, so this is all about de Broglie hypothesis and uncertainty principle. And so in the next class, we will talk about how we can develop a theory for quantum systems. So far, we only studied, the elementary things. That we raised the question, the de Broglie hypothesis and uncertainty principle will be 2 legs of the quantum physics. And we also came to know, or we also studied their importance. One will confirm whether a material particle will show its wave nature or not by checking the de Broglie wavelength with its corresponding diameter of the dimension of the system. And the second one, which is uncertainty principle, will tell you that non-zero ground state energy. That means the energy should be quantized. Okay. So, any question on today's lecture?
Sir, why that disparity is coming like 4 times the minimum energy we calculated by quantum model and the original energy? Why there is high disparity?
No, it's actually this is the exact process, right? As I said, Bohr's theory. So you have to do the detailed calculations, right? And you have this. And why the negative sign is appearing, I explained, because it indicates bound state. You cannot pull out electron from the atom. We cannot pull out the electrons. This represents the electron is bounded by the nucleus of atom. And because this is only qualitative calculations. The idea here is to show you that the quantum system should have never zero minimum energy. It should have non-zero minimum energy. And apart from that, all the physical parameters are variable. Mass, charge, pi, epsilon naught, h bar, whatever are appearing here. So these things are appearing here. Okay. And if you look here, similarly, h bar omega, okay, by using the uncertainty principle. And if you do the exact detailed calculation, we have h bar omega. So this case, luckily, we have exact value. And this case, we don't have the exact value. Okay, so that is not discrepancy, right? So because we are using uncertainty principle to check non-zero minimum energy. Some case, luckily, we get the exact value. Some case we won't, because we are using uncertainty principle. But we are not doing the exact calculation, right?
Yes, sir, got it. Thank you.
So any more question?
Sir, is it correct to say that wavelength is associated with the humans, but we cannot observe that wavelength?
Exactly. So if we move a velocity, we have u de Broglie wavelength as per de Broglie hypothesis, but the wavelength associated with us is very, very small comparison to the dimension of the system. And therefore, human being like we never show our wave nature. So that's why in the last class I said, the nature is, we are living in such a universe where the Planck constant value is 10 to the power minus 34. And if you go other universe, the Planck constant may be different. And in fact, the physics there is different, right? So who knows that, the creatures that might be living some other universe, they might have, shown their wave nature. Okay?
Yes, sir. Yes, sir. Yes, sir.
So any more question? So I forgot to upload the books. Some of the portion of the books I'll upload. In fact, you will easily get that book, Arthur Weiser from internet. It's a freely, I think, available. If you click, you will get it. This is very nice book, okay? And there are some other quantum physics book, Eisberg Rasnik, and this is one of your references book. So this is also very nice book. It is like a story kind of books, right? You find very less mathematical expression, but qualitative things. Okay. So tomorrow I am not going to conduct class, because if I start tomorrow class, then there will be like I can say I need to take the next consecutive class. Otherwise, you'll forget whatever I'll teach tomorrow, because you will have 1 week gap for your exam, and again will appear. So it is better. Let's on conduct class tomorrow. Tomorrow there will be no class, even if the next week, because of your exam, there will be no class. Okay. When is your exam starting?
Wednesday.
9th.
9th.
9th, right?
Yes, sir, 9th.
If I take class on Monday, will it be okay or?
So let's not take a class on Monday. Please.
Okay.
Yes, sir, please, sir. It would be
Okay.
very kind of you
Okay.
to please.
Okay. So if you allow me to conduct class on Monday, then tomorrow I'll conduct. Otherwise, as I said, I need 2 classes, right, to move in a good pace, right, in our current way. So since you have exams, so we'll not have class tomorrow. And then when we'll meet, then we'll talk about how one can develop theory for quantum physics and how we can solve quantum mechanical problem. As we have seen, right, the harmonic oscillators, the exact energy, the discrete energy levels, how one can derive that we'll also do. Okay.
Yes, sir.
So,
Okay, sir.
and
Yes.
regarding exam, everything has been notified by the exam section, but the question pattern, whether it is objective type or subjective type, that we have not decided. When I say we have not decided, that means other physics teachers. Okay. So, but by the end of Friday, I will let you know over WhatsApp. Okay. WhatsApp the detailed things, and most probably we'll have MCQ type. But at the same time, I cannot rule out the subjective type, because if the exam section will instruct us to conduct in a subjective type, then we will forced to conduct. Okay. So let me first discuss details with my colleague, and then I'll let you know over WhatsApp by the end of Friday or maybe tomorrow. Okay. But the syllabus is from the very beginning till the end of polarization. That means the entire topics inside unit 1.
Okay, sir.
Okay.
Thank you, sir.
Bye.
Thank you,
Thank you,
sir.
sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.
Bye, sir.